Maybe so.
Yeah, where is your screen?
It is on screen is already shown. Full screen.
Once it came, no? Ah, yeah.
I have some problems. Sorry, but can you hear me?
Yes, yes.
Okay, thank you. Can I begin now?
Yeah, please start.
Okay. Thank you again for having invited me and for being there. And again, sorry that I'm not present in person. Today is going to be a talk that's essentially the continuation of the previous one from yesterday. And the title is Morphic Sequences versus Automatic Sequences. We've seen yesterday these automatic sequences, remember? It was a question of a finite kernel. And we've also seen some sort of generalization of that. It was, remember, the binary Fibonacci sequence. The example of the famous example for automatic sequence was the so-called Prouhet-Tuomo sequence. Okay. I'm going essentially to give a survey based on several papers, one by Michel Deking, Martin Kevrek, and myself, one by Jeff Shadid and myself, and one by Michel Deking, Rim Yassawi, and myself. Sorry, there is a problem with the... I don't succeed in... Okay. There is some sort of delay. Oops. The connection is not very good. I'm sorry about that. Ah, doesn't work. Okay. Doesn't work either. Okay, excuse me. I will stop the sharing and share again, if you don't mind. Ah. Excuse me, there is a problem with the sharing the screen, and I don't succeed in getting my file. Ah. The file just disappeared. Sorry about that.
No problem. You can.
Yeah, I need 1 minute to repair that. Okay, the file just disappeared. I don't know what is going on. Sorry about that. What happens? Okay, sorry. I will just quit and come back in 1 minute.
No problem. You can even with 2 minutes, no problem.
Excuse me about that.
Hello, Sigiki.
He's not all. I think he's.
Hello.
Hello. Yeah, thank you for joining.
Japan becomes very hot lately.
Oh, I see.
Yeah. Maybe your place is a bit hot.
Yeah. Because your knee kata was better, I think.
But now I'm in the
Yeah, I know.
the Pacific side.
Yeah.
So what's the temperature around your place?
But this place, we are in Kerala somewhere. This is not that hot. It is maximum 28 or something. Maximum
Okay.
28.
Again, trying to get it now. Okay. And full screen.
That's great.
Okay. Seems to work, hopefully. Not quite. Okay. As I said, this is can you hear me?
Yes,
Yeah.
yes.
Okay. As I said, this is a sort of survey based on 3 papers that I already mentioned. And remember what we've seen yesterday was some results and some pictures like this, which is a variation on the Penrose tiling, not exactly the one we've seen yesterday, but a variation on it. And this is the column we've seen yesterday. I mean, we've seen the 4x4 and 8x8. This is the next one, the 16x16. And remember, there were some sort of special sequences hidden behind, automatic sequences and morphic sequences. So I'm recalling a few things that were already recalled yesterday and this morning by Shireki. When we have a finite set, we call this an alphabet. The elements of this finite set are called letters. And when you take a finite sequence or a finite string or finite block of letters, it's called a word. The set of full words on the alphabet A is denoted A star. And we have this stupid operation, so to say, operation, which is concatenating words. I mean, you have a word and another word, you just put them together, glue them together in the right order, and this gives you a structure, I mean, an operation which which gives a structure of monoid to A star, and this monoid is actually free. Free just means that you have nothing else than the unavoidable relations. For example, W square times concatenated with 3 is equal to W5, where over 2 means just that you have 2 blocks, 2 identical blocks concatenated together. The length of a word is the total number of its letters, and the empty word has 0. So remember, morphism, there was just a map from A star to B star, where A and B are finite sets, alphabets, and you want this map to preserve concatenation. Is that okay? Yeah. And of course, the morphism is determined by the values of A, because if you take a word, it's nothing but the concatenation of all its letters in the right order. And the morphism is called uniform, or of constant length, or of constant length L, if all the images of letters you started from have the same length L. Okay. Now, if you take a morphism from A star to itself, it may happen that this morphism is phi. It may happen that phi of A, or some letter A, begins with A, and the length of the iterates on phi on A tend to infinity with K. Okay. Then the sequence phi K of A tends to an infinite sequence that its limit for some either from some naive point of view. I mean, you have blocks, longer and longer blocks, and if you go farther, you get a sequence. Of course, you can say that in a snobbish way by saying that you take the topology of simple convergence, or even more snobbish by saying you take A, you equip A with the discrete topology, and then A star and even all sequences with values in A, this is a product of compact spaces. So this is a compact space by the Anagram theorem, and then you have the metric, the topology on it, which actually is even metrizable, but we don't need to do such things, such snobbish things, as we can see in the next slide. When you get this, when we iterate phi, you get something which is a fixed point, an iterative fixed point, as we saw yesterday. And this is called a purely morphic sequence. So remember the example of yesterday was either with plus or minus or with zeros and ones. So you have a morphism, 0 goes to 0, 1, and 1 goes to 1, 0, and iterating it means saying starting from 0, you have 0, then 0 goes to 0, 1, then the first 0 goes to 0, 1, and the 1 goes to 1, 0, and so on and so forth. So you get ultimately an infinite sequence, which, as I already mentioned yesterday, is a fixed point of the same map, actually the extension of this map by continuity. Another example that we have seen yesterday is the binary Fibonacci sequence. You see it's a little bit different. Remember, we had 0 goes to 0, 1, and 1 goes 1, 0 for 2 more. Here we only have 1 goes to 0. And if we iterate, we have an infinite sequence, which happens to be, it's called the binary Fibonacci sequence. By the way, a side remark, this sequence is Sturmian in the sense that was seen this morning, but of course not all Sturmian sequences are automatic because there are too many of them. There is another example. Okay, something more general than being a fixed point is that you have a fixed point and then you rename the letters. In other words, you call a sequence AN morphic versus purely morphic before. If you have an alphabet you start from, a fixed point on the alphabet as usual, phi infinity of that you iterate infinity often, giving you a sequence Bn, and then you have a map, a stupid map from B to A, and you take the pointwise image of Bn by the map, and you have a new sequence An. In the case the morphism you started from has had constant lengths, then the sequence is called constant length L, then the sequence is called L automatic. So maybe we're going to see an example. The Golay-Shapiro sequence, which was also called the Rudin-Shapiro sequence. I told you yesterday why it should be called the Golay-Shapiro rather than Rudin-Shapiro. Okay, you take an auxiliary alphabet to some point, A, B, C, D, and you have a morphism on B of length 2. A goes to AB, B goes to AC, C goes to DB, and D goes to DC. And thus, starting with A and iterating, you get a fixed point, AB, AC, AB, DB, and so on and so forth. And then you map this sequence letter-wise, letter by letter, saying, okay, I replace all the A's by zeros, all B by zeros, every C by 1, and every D by 1. And this gives you this pointwise image of the sequence on ABCD, which is a sequence on 0, 1, and which is actually the Golay-Shapiro sequence. It is, by definition, too automatic because the morphism in red in the middle of the page is of length 2. Okay, good. In general, there's no reason why a morphic sequence should, at the same time, be L automatic. You know, it could well be that you have a morphism, you take a fixed point, you take the image, and maybe the sequence you get could be obtained in a different way by some other morphism, some other pointwise image, except that the new morphism could be of constant length. Sometimes it's possible, very, very rarely, and sometimes it's not. For example, the binary Fibonacci sequence, remember, 0 goes to 0, 1, 1 goes to 0, is not L automatic, whatever L, larger than 2. Why? It's not extraordinarily difficult to show the following. Suppose you have an automatic sequence, and you look at some particular letter. If there is a frequency of occurrence of this letter, it may exist, it may not exist as well, but if the frequency exists, it must be, this is a theorem, it must be a rational number. Now, if you look at the Fibonacci sequence, it's not difficult to see that the frequency of 0 or frequency of 1 is not rational. It has something to do with the golden mean, with the golden ratio, 1 plus root 5 divided by 2, so typically not rational. So Fibonacci sequence is a typical example of a simple morphic sequence, and even purely morphic sequence, which is not L automatic for any L. Some people call morphism substitutions, as I said yesterday, and physicists call this kind of thing. How is it? Inflation rule. Yeah. Okay. And Cobham, in seminal papers dated 1972, called these sequences tag sequences. And automatic sequences by Cobham are called uniform tag sequences, but essentially nobody uses this terminology anymore. Okay. Now we can ask whether there are examples in the literature of fixed points of non-uniform morphism that are actually automatic. As I said, you have something that is generated one way with something with a morphism non-constant length, and you want to know whether it's possible to generate it in a different way with a constant length morphism. And yes, there's an example. For example, in 78, 79, there was a paper by Berstel. He looked at the square-free infinite sequence on 3 symbols, the Israeli sequence. You remember we have proved an easy result yesterday that it's not possible to find an infinite sequence on 2 letters without squares in it. Of course, on 3 letters, it might be possible, and indeed it is. And that was already done by Thue. And this one is an example of square-free sequence on 3 letters, fixed point of the following morphism. And Berstel proved that actually you can generate it in a different way. This time you start with an alphabet of 4 letters, what I call the auxiliary alphabet before. So 0 goes to 1, 2, 1 goes to 1, 3, and so on and so forth. Then you take the fixed point, and then you reduce mod 3 what you obtain. And you get essentially exactly the same sequence, except that in the first case, the morphism was not of constant length, and in this case, it has constant length too, so that the sequence is actually 2 automatic. And there are other examples in an old paper by Michel Deking in 1978. We're going to speak about that later on. So, continuing the story, Martin Kefelec and myself had a note in 2011 that was never published, where we proved a result that is not that difficult, that a certain morphism called the Listenermorphism, defined by A goes to ACA, B goes to D, C goes to B, D goes to C, so it's on 4 letters, which is actually, generates actually a 2 automatic sequence, namely the fixed point of the one written there, A goes to AC, B goes to AD, and so on and so forth. This is a case even more precise than previously. The first morphism is the first sequence. I mean, first way of generating the sequence makes it a purely morphic sequence, and then it's a fixed point of constant length morphism length 2 more precisely. Okay, the same result was obtained in 2017 by Grigor Shuk, Lenz, and Nagnibeda, and the Listenermorphism, I'm not going to enter into details. This is something that provides a representation by generators and relations, except there are an infinite number of relations, of a group which is called the first Grigor Shuk group. Maybe we're going to say a little bit about that in a little bit later. Okay, so that was an example of a sequence having this property, and we can find other examples by going to a very, very nice site. This is called the OEIS, Online Encyclopedia of Integer Sequences, that was founded by Neil Sloan years and years ago in a paper version. And this is a catalog of all integer sequences. Okay, come on, it's not a catalog of all infinite sequences because it would be an infinite catalog, but of all interesting, whatever this means, sequences of integers. So that if you have a few terms of a sequence of integers, you just go there, you put your terms into the side, and they say, okay, this sequence is a part of this infinite sequence and it has such and such properties. So it's a very useful tool and very nice tool. So for example, if we take the morphism 0 goes to 0, 1, 1, 0, 1, 0, and 1 goes to 0, 1, if you take the fixed point, doing some sort of nasty things, you can prove that the fixed point is 4 automatic, which is the same as being 2 automatic. Maybe I forgot to say that yesterday. Something is D automatic if it is D squared, D cube, D4, whatever, automatic. And this is if and only if. Okay, so there is a way by doing some manipulations, which are written there actually, to prove that the fixed point of this morphism psi, which the morphism is not of constant length, but the fixed point can be generated by a morphism of constant length and so that the fixed point is 2 automatic. 4 automatic, actually, 2 automatic. Okay. And as you can see, the image by psi of the 0 and of 1 are obtained by concatenating anagrams of the word 0, 1. So you have either 0, 1 or 1, 0. Okay. And this is very general situation where we could state Martin Kefelec, Michel Decking, and myself a theorem that we call Anagram Theorem. So you have a finite set of anagrams, that words having exactly the same letters but maybe in a different order, and we have a morphism on A with a fixed point, and you suppose that the image by psi of any letter is a concatenation of words in this set of anagrams, like on the second red line on the slide. And then the theorem says, then the fixed point you obtain is D automatic, where D is the length of psi of W divided by length of W. And of course, it doesn't depend on W because as we say, W belongs to a set of anagrams of a given word. Okay. And before going to another theorem, more ancient and more general, we claim that this anagram theorem gives a sort of visual proof, visual way of getting the automaticity of some sequences that are in this encyclopedia. For example, the sequence number 28, 48, 78 in this encyclopedia define that the fixed point of the morphism 0 goes to 0, 1 and 1 goes to 0, 1, 1, 0. You see the anagram 0, 1 and 1, 0 is 3 automatic. That's immediate from the anagram theorem. Same thing for other sequences for which I give the numbers in the encyclopedia. Another example is the sequence 28, 52, 49, where define something which is a limiting word, zero limiting word of some morphism, but that is a fixed point actually of the square of the morphism. Penultimate line, you see 0 goes to 0, 1, 0, 1, 1, 0, and 1 goes to some very long word. And applying this theorem, you see that you have essentially anagrams 0, 1, 0, 1, 1, 0, 1, 0, 0. So those are all anagrams of rank 3. And if you apply the theorem, you get that the sequence is 9 automatic, and 3 automatic. As I said, 9 is just 3 squared. Okay. Same thing for the sequences in this encyclopedia. It happens that there was an old theorem by Decking, it's 1978, that sort of supersedes the anagram theorem. It was published in the Zeitschrift für Wahrscheinlichkeitstheorie und verwandte Gebiete, and this journal changed its title to translation into English, which is Probability Theory and Related Fields. And okay, the theorem looks a little bit technical, but essentially you take the length of all the images by the morphism, that gives you a vector, and you have a matrix that is naturally associated with the morphism. It's called the incidence and transition matrix, whatever. And then you just look whether this vector is a left eigenvector of the matrix. If yes, if so, then the sequence is Q automatic, where Q is the modulus of the largest eigenvalue, that is the spectral radius matrix. Okay, so this is perfectly computable, if I may say. You have your morphism, you compute the incidence matrix, whatever that is, easy to see. You take the vector of length of the psi of different points that you are looking at, and if you have a left eigenvector of the matrix, then the sequence is automatic. It's not difficult, it could be an exercise to prove that the so-called anagram theorem is a consequence of the Decking theorem just mentioned. But the theorem of Decking is strictly stronger. For example, if you look at this morphism of non-constant length and you look at the fixed point, the fixed point is 3 automatic. And as you can see, there is nothing like anagrams hidden in this, but Decking theorem gives the result. Okay. Maybe I should say a word as promised about self-similar groups. And this is taken from the book by Nekrashevich in 2005. which is a nice book on the subject. Essentially, you construct groups using automata, and it gives you examples, non-trivial examples, of groups having some non-trivial properties. Okay, that's essentially what he says. And he gives an example of the group I mentioned previously, Grigorchuk group, that you can define very simply with an automaton. And this group has an interest because it's an infinite finitely generated torsion group. And furthermore, it's the first example of a group whose growth is interpreted between polynomial and exponential. Okay, whatever this means, again, we have this property. It's not exactly automatic sequences there, but something related to automata, that you have something between order and chaos, remember, periodicity and randomness, so to say, a little bit closer to order. And furthermore, simple, which maybe I didn't say yesterday, constructing something with automatic sequences or with automata is a simple construction, whatever this means, but it can give non-trivial results. And that's the who interest or this kind of structure. By the way, there is another notion that I show, which is automatic group, and it has essentially, it seems to have no relation to automatic sequences, versus automata groups have relations to automatic sequences. Anyway, okay, if we look at the self-similar groups in the literature, they are given by morphism of non-constant lengths, and some of them, corresponding fixed points, happen to be automatic. For example, the Listenermorphism that we have already seen happens to be too automatic, although it's defined by a non-constant length morphism. The group studied by Bartholdi and Grigorchuk has essentially a same kind of generating morphism, is actually too automatic. And there is an example in the thesis, PhD thesis by Muntian, A goes to A, B goes to C goes to B, which again gives an automatic, two automatic sequence. Okay, at this point, we have at least two natural questions. One is, what were self-similar groups? Do we have examples of self-similar groups defined by morphism whose fixed points are not automatic? And the second question, which is maybe more interesting, some fixed point of non-constant length morphism are automatic. So if we look at all these special morphisms of non-constant length giving actually automatic sequences, what kind of sequences do we get? What kind of automatic sequences do we get? You see, you have all these morphic sequences. You take the subclass of all of them such that the fixed point can also be generated in some automatic way. What kind of automatic sequence do we get? Maybe we can twist a little bit this question. Instead of taking fixed point, you just take morphic sequences. So we have non-uniform morphic sequences, which are morphic sequences for which the defining morphism is not uniform, not of constant length. Some of them are automatic. If you look at those, which subclass of automatic sequences do we obtain? The answer to the self question is not very difficult. The answer is yes, indeed. There are some examples. Okay, difficulty is essentially to prove that a given sequence is not automatic, and it will be addressed in the next part of this talk. Exactly, how to prove that a non-uniform morphic sequence is automatic. Caveat, when I say non-uniformly morphic sequence, it's not uniformly morphic sequence, it's a non-uniformly morphic sequence. That means it's given by a non-uniform morphism, but it might well be that there is another way of generating it. It's a property of the sequence, not of the morphism. Okay. The question, twisted question, question 2 prime, I remember it, I recall it, some non-uniform morphic sequences are automatic. What are these automatic sequences? Answer, sort of unexpected, all. All automatic sequences can also be generated by morphism plus projection, where the morphism is non-uniform. Okay? In other words, non-uniformly morphic sequences contain all automatic sequences. Okay? And this is the paper by Jeff Shalit and myself. Any automatic sequence is also morphic in a non-uniform way. And okay, I give an example. I was trying to give an example for two more sequences, but maybe it's too complicated. Yeah, of course, we don't have the right of cheating. This example is non-uniform. It generates more sequence, but it's just cheating because 2 never occurs. If you start from 0 and you iterate, you never have the 2 occur. So cheating is forbidden, if I may say. And the idea I gave, I mean, maybe we could skip that. Actually, we take the power 4 of the foremost morphism, and we split gamma of 0, 1. Okay, I mean, this is purely technical, and it gives also the idea why the result, the very first line of this slide is true. Maybe we can skip that and just remember the result. There was a previous example in the literature. Doesn't work. Oops. Sorry, the connection is not good again, but it will be okay in a minute. Yeah. Okay. Yesterday we spoke about the Tower of Hanoi Tower, and we say that there's a sequence on a factor of 6 letters, A, B, C, with A bar, B bar, C bar, which are the moves from the first peg to second and so on and so forth, and the backwards reciprocal moves. And it was proved by François Dresse and myself many years ago that this sequence is actually a fixed point of this morphism, but it happens also to be the fixed point of a non-concentric morphism that you can see at the last line of the slide. Okay. Just to say that, okay, there are several ways of generating classical sequences, and some ways are sort of easier than others, and it's just a question of point of view, maybe, which one is simpler. Okay, so I'm stuck again. Oops. Okay, how do we prove non-automaticity of a sequence? And this is in the paper by Jeff, Remia, Sawi, and myself. First of all, we can go to the very definition we gave yesterday. We look at the kernel, the Q kernel, and we prove that this is not finite by exhibiting an infinite number, an infinite set of sequences, of subsequences in this kernel. An example which we are going to see later on is A goes to AAB, B goes to B. This is a bizarre example. Okay, we see that later. And this is the set of sequences Vn that we have to look at that belong to the kernel, to 2 kernel, and that are not in a finite number of them. I mean, there is an infinite number of them. Another thing is to look at the frequencies. I mentioned that just previously for the Fibonacci sequence, binary Fibonacci sequence. The block complexity. Block complexity is number of blocks, of strings, of factors, if you want, of given lengths. It was also mentioned this morning. If we extend the automaticity to 2-dimensional sequences, which I mentioned briefly yesterday, and you take the Pascal triangle mod D, and you want to know whether it's K automatic for some K, the answer is, if D is a power of a prime number, then you have a P, this prime number, a P automatic sequence. And if not, the sequence is not automatic, whatever D is. Typically, if you take D equal 2, 3, 4, those are prime powers, so it's 2 automatic, 3 automatic, and 2 automatic. For 5 also, it's 5 automatic. For 6, it's not automatic because there are 2 different prime numbers in 6, and it's not K automatic, whatever K is. Okay. There is another thing. If you look at the rows of the gaps, things like this. It was already in the seminal paper by Cobham. And for example, this can be used to prove that the characteristic function of the primes is not K automatic, whatever K is. I mentioned yesterday a Dirichlet series. You remember we took the Morse sequence with values plus or minus 1, and I claimed that there was a continuation of this to the whole plane, the whole complex plane, giving an entire function. For a general automatic sequence, it's slightly different. It can be extended to a meromorphic function with poles, possibly poles. And these poles, if any, have a very special structure. They must be located on a finite number of half lattices on the left. So you see what a lattice is, you see what a half lattice on the left is. You can have only a finite number of them. Poles are necessary in a finite number of these half lattices, so that if you find a Dirichlet series and if you are able to obtain the meromorphic continuation of this series, and if the poles don't behave correctly, are not on this kind of structure, then you can claim that the sequence you started from is not automatic for automatic for anything. Okay. We can also look at the properties, the orbit properties. So we take the sequence, the shift sequence, where you kill the first term, then you kill the first two terms, and so on. This gives you a set of sequences, and you take the closure for the topology that you are using, and this is called the orbit or the closed orbit, and it must have some properties. And last but not least, there is a nice generalization of the theorem of Cobham by Fabien Durand. Since I did not mention this Cobham theorem yesterday, let me give a quick word on that. The theorem says you cannot have a sequence that is simultaneously 2 automatic and 3 automatic, except if it is trivial, that is, if it's ultimately periodic from some point on. Okay? It's not possible to have a non-trivial sequence being both 2 automatic and 3 automatic. And you can replace 2 and 3 by P and Q, where property of P and Q is that they are multiplicatively independent, which means either that no power of P is equal to a power of Q, or if you prefer, the quotient, the ratio of log P by log Q is irrational. Okay, typically 2 and 3. And there are many other ways of proving non-automaticity. So I mentioned here some funny things that actually some of them were mentioned already yesterday. For example, it's not difficult, and it could be an exercise to prove the 2 more sequence defined with the morphism. Remember, 0 goes to 0, 1, 1 goes to 1, 0, has no cube in it. The other one, you remember, this was the Prouet result that was called the Tarrier-Scott problem. Till Wright rediscovered the paper of Prouet. And yeah, the Golay-Shapiro sequence. Remember, we started from an alphabet with 4 letters. We had a fixed point, and then we replaced A and B's by zeros and C and D's by 1. And result, if you take the supremum for all theta of this bizarre quantity, absolute value, then you get something which is between root n and some constant times root n. I mentioned yesterday that if you take any sequence instead of the -1 to the n, any plus or minus 1 sequence, on the left, you always have root n because the infinite norm is larger than the L2 norm, and the vectors are orthogonal. And on the other side, on the right, the trivial bound n is not a big deal to get. And if the sequence is random, whatever this means for almost all sequences, you have root of n log n. So that this sequence, the Golay-Shapiro sequence, has a property of this quantity between the 2 inequalities is as small as possible between root n and constant root n. So it essentially behaves like a random sequence. Okay, although it's clearly not random, whatever definition of randomness is, because you generate it by this morphism. I mean, this whatever definition of randomness is, this is certainly not a random sequence. Okay, and this is interesting in another way, because if you look at something which is called the spectral measure of this sequence, you get the Lebesgue measure. So the same as if you have taken a purely random sequence, whatever this means again. Okay, so the Golay-Shapiro sequence is amazing because it essentially behaves as a random sequence for a lot of of properties, but of course not for all, because it's definitely not random. Now, I promised to say something on a morphism that we have seen previously, which was as follows. We can define how to define the integers. You have the piano axioms. You have also a sort of, if I may say, almost snobbish manner, this Bourbaki manner. You don't want to define the integer, you define the sequence of sets, and then you say that the cardinalities of these sets is essentially the set of natural numbers. How does it work? This is due to von Neumann, essentially. You start from this empty set, you call this A0, then you take the singleton, the set reduced to one element, and the element is the empty set itself. Then you take the set with two elements, which is the empty set and the singleton empty set, and so on and so forth. And so maybe to make things a little bit more symbolic, we replace empty set by two braces with nothing in between, so that A0 equal open, close, A1 is open, close, closed, A2 is open, closed, open, close, close, and so on and so forth. And the usual definition of the integers, I mean, the snobbish definition mentioned is, okay, I call 0 the cardinality, I call cardinality of the first set 0, I call the cardinality of the second set 1, and so on and so on. If you look at this, since it's complicated to type this braces opening and closing, replaced by A and B. So AB, AABB, AAB, AABBB, and so on and so forth. And you can prove that the sequence of roots converges to the fixed point of morphism we saw previously. A goes to AAB, B goes to B. So there's a morphism hidden behind the snobbish definitions of integers. And remember, we have seen that the sequence was not too automatic. It was sort of complicated. We had to take some family of sequences in the kernel. And from a result by Fabien Durand, it suffices to show that it's not too automatic because the largest eigenvalue is 2 or something like this for this morphism. So that once the difficult thing is to prove it's not too automatic, and then you get everything almost for free. Good. You remember the Penrose styling I mentioned intensively yesterday. This is not exactly the one of yesterday, but this is a variation on it. Remember, there was something discovered in the 70s. It's a paper by Penrose, who wrote Aesthetics in Pure and Applied Math, was in 74. And remember, there was those worms inside, a sequence of bow ties, short and long, which was given by the Fibonacci sequence. And you remember that 10 years later, in 84, this was this discovery by Schleichmann, Blaise, Gracias, and Kahn of an alloy of aluminum and manganese that was quickly frozen. And that was doing that, you obtained material for which the atoms, when you make a X-ray diffraction scheme, you've got atoms disposed in a way that is somehow similar to this tiling, and this is forbidden in the classical crystallography, so it's not a crystal, and it's all the things about quasi-crystals that become famous afterwards and seem to be abandoned, at least from a theoretical, I mean, from a practical point of view. Oh, by the way, there's an anecdote I didn't tell yesterday. You know, when you say you're doing mathematics, people immediately ask you, why do you do that? Why do you do mathematics? Are they useful for something? What is the use? What are the applications? But I mean, if you work in any field other than mathematics, people never ask you about that. If you say I'm studying ancient Sanskrit, or if you say, I don't know, I mean, if I'm studying the biology of worms, real worms, nobody asks you. But if you say I'm doing mathematics, people immediately say, oh, what are the applications? So I was happy at some point people found an application of the Penrose tiling set of the quasi-crystals. They made a material that was conducting easily the heat, was strong enough, and blah blah whatever. And so they made frying pans. with quasi-crystals. So I could say, you know, there is an application of that, except that it was a failure. I mean, commercial failure. They stop producing it very quickly. I don't know why. And so nobody has, as far as I know, applications for the everyday life of quasi-crystals. Okay, it's not a big deal. We usually don't care about applications. Of course, we are very happy there are some applications. Okay, remember it has something to do with the Fibonacci morphism. Okay, I spoke about Kalam or Kolam or Kangoli, what the other word?
Rangoli.
Yeah, thank you. So remember, it has to do something. It has to do with the two-more sequence or variation of the two-more sequence, and I'm quite sure that other Kalams could be described with such automatic sequences, except that many of the Kalams I've seen are not are just finite. I mean, they are not extendable infinitely, to my knowledge. I don't know much about these. And this one has to do with the Morse sequence. Breaking news. There was a paper, when was it? In March this year, giving a necessary and sufficient condition for a morphic sequence to be automatic. Remember, we had a sufficient condition that was the decking theorem, or a more tractable theorem that was the anagram theorem that says, okay, you look for a vector, the eigenvector or something, a matrix, blah, blah. And except that this necessary and sufficient condition is not for all sequences, but only for the uniformly recurrent sequences. What does it mean? The sequence is called uniformly recurrent if each time you see a block of consecutive letters in this sequence, you are sure that you are going to see the block infinitely often, and that the distance between two occurrences is bounded for a given block. Okay. In other words, you take a window of size D, you put the window somewhere. Oh, I see a block. Okay, now I travel the window. I'm sure that I'm going to see the block infinitely often, and that I'm not waiting to wait too long to have a new occurrence of the same block. Okay, so for a given block, the time you have to wait is bounded. Okay? In particular, for a morphic sequence, if the matrix, transition matrix that I did not define formally, but you can have a vague idea of what it is because it's called transition or incidence matrix. If this matrix is primitive, then the sequence is uniformly recurrent. And primitive for a matrix, you know, that means that there is a power of the matrix. Yes, a matrix with integer coefficients. And there's a power with positive, non-negative coefficients. There's a power for which all the coefficients are positive, strictly positive. This is a paper by Elżbieta Krosik and Clemens Müllner that appeared on the archive in March 2023. I don't think it was published yet. And it's called Automaticity of Uniformly Recurrent Substitutive Sequences. Yeah, this is a very nice paper. Elżbieta Krosik is going to defend her thesis, PhD thesis in September or something in Krakow, I think. And yeah, actually, they do even more as far as they say in the paper, or as I say orally, I forgot. They claim that they know how to change, to modify their proof so that it works for any sequence, not only the uniformly recurrent sequences, but for any sequence. And this would be another breaking news because it essentially kills the survey by taking Yasawi and me, saying how to prove that the sequence is, taking Kefelek and me have to prove that the sequence is not automatic. This would give the ultimate result on that. Okay, maybe I should stop here and wait for a question if any. And Andy, thank you very much.
Question?
If you have no question yet, of course, you can write me. You have my email address, and I would be very happy to answer these questions, if any, as I was very happy to give this talk here.
Okay, then. Meet tomorrow.
Okay, thank you. See you tomorrow. About music.